Hey everyone, my name is Shir Sahare. I'm a part of Team 2 working for Parlay Finance as a part of my Capstone project. So in today's presentation, I'm going to take you through project overview, working of the system, our current progress, our key findings, conclusion, and future work. So in the current loan classification system, we're using multiple models which often lead to inefficiencies. And there are several challenges faced, including diverse applicant profiles, past data, and in order to deal with this, we need a single, reliable, and scalable machine learning model. And as a part of this project, we aim at developing an AI-powered loan fit scoring model to predict the loan eligibility. So this process starts with gathering applicant data, which includes several applicant profiles, which contain key financial and business details. We also aim at generating synthetic data to expand training data sets. This data actually has around 45 plus financial and risk parameters, ensuring comprehensive loan assessment. Coming to eligible loan types, uh, in this project, we are particularly focusing on four loan types, namely 7A, 7A Express loan, 504, and 8A loan. And finally, coming to applicant fit, we're going to evaluate that using a single multi-class multi-label model. And in the future scope, uh, we aim at developing and enhancing the machine learning models by integration of additional financial parameters. So in the working of the system, we generated data which was based on the data set provided to us, the synthetic data provided to us, and this data was generated on predefined business patterns such as revenue patterns, which were categorized into growth, decline, boost, or sharp decline for controlled randomization to get realism in a data set. And we were also provided with the loan eligibility function by Parlay Finance, but later on we got to know that there were a lot of flaws in that function. So we built an automated eligibility function, Python function, to assess financial health, credit scores, business tenure, and collateral to classify applicants based on SBA loan criteria. And these were the following loan types and the eligibility criteria. In the end, with the help of ChatGPT and other LLMs, we were able to generate around 200,000 plus synthetic business records, ensuring there was financial constraints. We also ensured the fact that we were filtering the DSCR values between 0 to 2.5 to maintain realistic financial conditions. We were also faced with a lot of challenges. Most importantly, the overfitting challenges, which was mostly attributed to class imbalance, and the model, instead of learning underlying relationships, it was just learning the memorized patterns in the synthetic data, which also led to the problem of label generation, because assigning accurate loan labels was difficult, as some of the applicants met multiple loan eligibility criteria while others barely met any, which can make classification ambiguous or on real world data sets, because since we are only working with synthetic data right now. So we decided to hop back into exploratory data analysis to find out what exactly is happening with the data and why are our machine learning models performing abnormally good. So we found out that there was a strong positive correlation which existed between annual revenue, uh, NOI, and DSCR, which indicated that the businesses with high revenue tend to have better financial health. And in the case of debt and revenue, it showed moderate correlation, while in case of personal and business credit scores, they showed weak correlation. Coming to data balancing, which was one of the most important problems that we faced while doing the project. The dataset had a significant class imbalance, which might cause bias in the machine learning models and favor the majority class. So we took several steps to deal with this. First of all, for dealing with numerical features, we applied SMOT, also known as synthetic minority oversampling technique, which is usually used for numerical features to generate synthetic samples and improve representation of the minority classes. In case of categorical features where SMOT doesn't work, we applied random oversampling to balance the feature distribution. Last but not the least, we also performed final capping of each class, which was capped at 12,000 samples per class to prevent extreme overrepresentation of any other class, as we can see over here. Then we come to the key findings. We performed classification task using the neural nets or MLP model. This was the model architecture, used batch normalization, dense layers, and leak relief along with dropout. And the features used for engineering included risk score calculation, express fluent score adjustments, and polynomial and log transformations. And these were the results we got. We detected that there was a slight overfitting in the ET category, which required further adjustments. But in case of ineligible class, the recall was improved 57%, and the model generalization often remained stable across training, validation, and test data sets. Coming to XGBoost classifier, um, it also had the same features for feature engineering, and we also included hyperparameters such as learning rate and max depth. And these are the results that we got for XGBoost classifier. It performed fairly well. It gave a balanced performance across all datasets with no significant overfitting, and it also gave like a high recall for 504 express and 7504 loans. And in case of ineligible class, the F1 score was increased to 0.8, which was previously 0.71. Coming to LightGBM classifier, this was one of the best performing models that we had, and it gave stable performance across all data sets. It also improved the recall for 504 express and 7A for 504 loans. But in case of ineligible class, the recall remained low at 56% compared to XGBoost 66%, which clearly indicated room for improvement. Coming to the last but not the least, the TabTransformer model, which is a hybrid deep learning model which combines embedding layers and transformer encoders for categorical data. This model was optimized and trained with RADM and look-ahead optimizer for faster conversions, and we also use cosine annealing LR for learning rate for better generalization and a dropout of 0.7. And in this case, we also got an improved recall for 504 express and express loans, which was done by minimizing the false negatives. And we also achieved a strong precision and recall for the ineligible class, effectively minimizing the bias. So these were all the models. So in conclusion, these were all the models we ran till now, in which we found out that XGBoost and LightGBM achieved the highest accuracy of 87%. TabTransformer demonstrated strong generalization, which can be seen through the 85.9% accuracy that it got, and excelled in handling categorical data. Neural networks can perform better, given that we do more hyperparameter tuning to prevent overfitting. But all in all, a LightGBM offered the best balance between speed and interpretability, making it a well-rounded choice, and it respected the trade-offs. And in the future, we aim at incorporating time series revenue patterns for advanced feature engineering, hyperparameter optimization for in case of neural networks especially, and we also aim at implementing a hybrid ensemble model, in which we develop a stacked ensemble combining all the models that we discussed earlier to enhance the overall performance. Thank you so much.